Well, we will continue our discussion. We'll wrap up the lecture part of this course. And again, as I told you earlier, that the topics that we cover in chapter 11, 12, and 15, there are only a few questions related to these three chapters. There may be one or two questions about the assets, about the asset base, and about the not even about the internal forces there. So 11 and 12 are not on the final exam, but 15 there's a couple questions in there. So when we get to that point there, I will point out these are the things that we do expect to examine. Okay. So before we jump into chapter 15, we want to continue our discussion on chapter 12 there. And we were talking about the solution, the behavior of the solution yesterday, and we finished the first learning objective there. So in the first learning objective, we gave you some definitions about the solution. We talked about like dissolves like, which is a very important concept there. And we told you that polar bear will dissolve in water because water is polar. So that's the whole idea there. All right. And when you work on the homework questions there, if you are going to be looking into chapter 12 and working on problems after the final exam, which I sincerely hope that most of you will, because after this class, what's left? It's just summer, and it's time for you to go to the beach, and you should take your chemistry books with you, and while laying on the beach and having a great time, and read your chemistry books there. Okay. So if you're looking through the homework questions assigned in that chapter there, we ask you what can be dissolved in what, and then remember that principle there, like dissolves like. Okay. So talking about the behavior of solutions, we are making comparison between the behavior of solution to pure solvent. Okay. So what happens if you have a cup of water? And what happens to the freezing point, the boiling point of water compared to if you dump some table salt in there? Okay, so that's something that we want to look into. And in order to study those different properties, I mean the difference between the behaviors of solution versus the pure solvent, we introduce another measurement for concentration. And this time it's a small m, capital M. Capital M was for molarity, M-O-L-A-R-I-T-Y. And this time we're talking about molality, M-O-L-A-L-I-T-Y. M-O-L-A-L-I-T-Y. So molality, by definition, is the number of moles of solute per kilogram of solvent. Now molarity, by definition, that's the number of moles of solute. That part is the same, per liter of the solution. So the key difference there is in the denominator. In the denominator for molality, the new concentration measurement that we're introducing here, we're talking about the mass of the solvent. In chapter 4, when we introduced molarity, we were talking about the total volume of the solution. Now there is a subtle difference there. Actually, if you watch on the result when we ask you to prepare a 1 molal solution versus 1 molar solution, actually the volumes are different. Okay, so this is how we define molality. Small m, a number of moles of solute per kilogram of solvent, and then number of moles is mass over molar mass. Okay, so rearranging the equation there, you have 1, 2, 3, and molality. Total of 4 quantities involved in this equation. If any of the 3, any of the 4, if among these 4, if any of the 3 are given, well, you should be able to figure out the 4th one. Again, we're going back to the calculation part where it's just dimensional analysis. And using dimensional analysis and setting up the conversion, and knowing the definition of the molality and using the conversion factor, you should be able to do, we need you to be able to calculate the quantities if all the others are given. So in this particular equation, remember, when the basic definition appears, there are only 3 quantities in there, but there is a relationship between the mass and molar mass there. So we can introduce the molar mass in this equation there, a total of 4 quantities. If 3 of them are known, the 4th one, we should be able to calculate the 4th one. Okay. So talking about the molality versus the molarity, well, the key difference there is that molality in the denominator, it's the mass in kilograms, mass of the solvent in kilograms. Okay? And when we express these different types of concentrations in chemistry, their molarity, the one that we have talked about before in chapter 4, we use a capital M. Okay? Molality is a small m. And then we call it a molar solution. And this is molal. Subtle differences there. Now, is there a difference between these two different concentration measurements? Well, the answer is if we ask you to prepare a 1 molar solution or a 0.1 molar solution of a particular compound there, well, you measure out 0.1 mole of that solid, and you put it in the bottle, and this is something that we did in the titration lab. You put certain amount of the solid in the volumetric flask, and you add water. Now, when you add water, the total volume of the solution would be 1 liter. So after you put the solid in there, you add the water to the mark on the neck of the bottle there, where the meniscus rests right on that mark there. This is a 0.1 molar solution. The total volume would be 1 liter. But if we ask you to prepare a 0.1 molal solution, well, you put the same amount of solute in there, 0.1 mole. But now you need to put 1,000 grams of water in there, 1 kilogram of water. Now, if you mix the two together, you will see actually on that bottle, the total volume of the 0.1 molal is a little bit more than the 0.1 molar solution. So that's the difference there. And again, in the denominator, it's the volume of the solution versus the kilogram, the mass of the solvent in kilogram. And the new concentration that we introduced here, in the denominator, we have mass in kilogram, mass of the solvent in kilogram. So these are the different types of measurements there, and we, when we talk about the in terms of concentration there, and then this is the molality. Then we will be focusing on the unit moles per kilogram. And that is for every kilogram of the solvent, how many moles of the solute is dissolved in the solution. Okay. Now, for things like this, and once we know the definition there, we can ask you to do some calculations there. So here, if you have 4.5 gram of naphthalene, you dissolve it in 95.5 gram of carbon tetrachloride. What is the molality? Well, in order to do this kind of calculation, you have to know how we define it. And once you know the definition, well, we can go with the definition. Here, we have 4.5 grams of naphthalene. And we want to convert it into moles first, and according to the dimensional analysis that we do here, 1 mole equals 128 grams. Well, 6.2 there. So we plug in the conversion factor, and once again, we're doing the dimensional analysis. When you do this calculation, you can see gram and gram cancels out. Now we'll give you the number of moles of the solute. And then, by definition of the moles of solute divided by the kilogram of solvent. So we have 95.5 gram of carbon tetrachloride. Well, we've got to convert it into kilograms. So 1 kilogram equals to 1,000 grams. And gram cancels out. So that will give you the answer for this question there. So in order to be able to do this kind of question there, calculation there, you have to know how we define molality, and that's what's important there. Okay, so gram has to be converted into kilogram, and you end up with mole per kilogram. So that's the ending unit there. And if you plug in the number correctly and you do the calculation, you end up with the molality of the solution will be 0.368 moles per kilogram. So again, the calculation involved in here really isn't nothing. It's just dimensional analysis. Nothing new here. As long as you know how to use conversion, how to identify the conversion factor, how to plug them in, then the calculation is easy, and the calculator will do it for you. Okay. Another type of question here is that we can ask you if you want to prepare a solution with 0.450 molality, and the total volume is 500 milliliter. And how many grams of ethanol do you have to put in there? You can calculate the molality there. Now, this particular calculation there, this particular question there, we assume you know the density of water is 1 gram per milliliter. So a 500 milliliter will be 500 gram, 500 gram will be 0.5 kilogram. All you need to do is to figure out how many grams that we need. Now remember that equation on the first slide there. We say, well, we need to know there are 4 quantities involved in here. Okay, so in this case, mass is involved. We are trying to figure out the mass. And what we know here is that the molality equals to 0.450. Okay, that's moles per kilogram, the unit there. And that should equal to the number of moles of the solute. Now, we don't know how many moles we have here. So we don't know how many moles, we don't know how many grams. But we know number of moles divided by the kilogram of the solvent will give you this answer here. So we have 500 milliliter converted into 500 gram, and that's water. Okay, so 1 gram per milliliter and times 1 kilogram per 1,000 grams. So gram and gram, this is for the water part in the denominator. Okay, on top, we need to figure out the number of moles. Well, you have X gram so if you don't know how many grams of ethanol that you need to measure out, assume it's X. X times the molar mass, 1 mole equivalent to 46 grams. In this case, gram and gram will cancel out. So basically, X is your unknown. You get the moles on there. And if you plug in the number correctly and calculate figuring out the X there, it's 10.4 grams. So you need to measure out 10.4 grams of ethanol, put it into 500 milliliter water, you get the concentration. And so these type of calculations are very much similar to the molarity calculation that we talked about in chapter 4. And you just have to know the definition in order to be able to answer these type of questions there. And again, since this particular topic is not going to be on the final exam, after the final exam, if you have some time there, make sure you go over these calculations there. And this is a topic that we need to cover in either General Chem 101 or General Chem 102. And I know on this campus here, we include this particular topic in Chem 101. Now, we do not test you. The American Chemical Society first term chemistry exam does not cover this particular topic. We don't talk about this topic in Chem 102. And those people who are taking Chem 102 later on this semester, in the summer, at the end of the Chem 102, you will be given another ACS test. Well, I can't say that for sure because that depends on the instructor there. The 2 instructors, they are going to decide in the summer whether or not they're going to use the ACS exam. But if they do choose to use ACS exam, then you will see topics related to the molality on that exam. So, I just remembered there's a conversation between me and the other 2 instructors because I was coordinating the Chem 102. So I told them in the regular semester we use ACS exam as a final exam, but in the summer, and it's their call. And if they decide to use it, well, then expect to see questions related to this particular topic and those people who are taking Chem 102. Okay, and another type of question here, we can give you concentration in percentage. So we'll give him a percent concentration, and we can ask you to calculate the molality here. Now here's an example. If we ask you to figure out the molality of a 28% aqueous ammonia solution. Now, yesterday when we were talking about chapter 11 there, when we're, well actually it's chapter 12 there, when we're talking about in the first learning objective, when we say when you see the word aqueous, that means the solvent is water. Okay, so you have 28% aqueous ammonia solution. What does that 28% mean? And we would assume in this case, and the question should say 28 by mass or 28 by volume, we would assume 28% by mass. So this means if you take 100 gram of the solution, and you would have 28 grams of ammonia, and you would have 72 grams of water. Okay, so that's what that 28% by mass means. So in this case, we can assume if you take 1,000 gram or kilogram of this particular solution, you would have 0.28 kilogram of ammonia, 0.72 kilogram of solvent, water. So here, based on that information, we can figure out the mass of the solvent. And we also know the mass of ammonia. Molar mass for ammonia is 17 grams per mole. So if you know the mass, and you know the molar mass, you can figure out the number of moles. Okay, so if you have, say, if you take 1,000 gram of the solution there, you would have 280 grams of NH3, ammonia dissolved in there. And then each mole is 17 grams. In dimensional analysis, gram cancels out. And then on the denominator, 0.72 kilogram of water. So this is assuming you have 1 kilogram of the solvent there, and 28% by mass will give you these information. And plug in the number correctly, and you do the calculation, and will give you roughly about 23 molar. So that's another type of calculation. Again, everything that we showed here has something to do with the definition. You got to know the definition, how to define the molality, and that's very important. Okay, and so that's our introduction for the measurement of the solution there. Now, why do we need that quantity here? Because the behavior of the solution varies compared to the behavior of pure solvent, and that difference in terms of the behavior of the solution versus the solvent has something to do with the molality. And that's the concentration. It has something to do, some of the properties there of the solution depends on the number of particles dissolved in the solution there. So this is this is the time that we need to look into the relative number of particles dissolved in the solution. So the next learning objective that we're going to get into here is that we need you to be able to describe what we call the colligative properties of solution, namely vapor pressure. How does the vapor pressure change when you compare a solution versus a pure solvent? How does the boiling point change? How does the freezing point change? And what about the osmotic pressure? Those are the 4 properties that we want you to know. When you have a solution versus a pure solvent, and they're going to behave differently on those 4 different properties there. And also, these are the calculation, the equations that we want to introduce there. And there is a freezing point change. The freezing point of the solution, it will be different from the freezing point of the pure solvent. So we say there's a freezing point depression. The freezing point of the solution is lowered, and boiling point elevation, and boiling point of the solution is higher than the pure solvent there. We can actually quantify that change in temperature in terms of the freezing point and boiling point. That change in temperature is having a linear relationship with the molality, the concentration that we just talked about. So if you can figure out the molality there, and you know the constant for the particular solvent that we're using, you can figure out what's the new boiling point of the solution, what's the new boiling point, freezing point of the solution. Okay, so that's the calculation involved in here. Now the colligative properties there is that some of the physical properties of the solution, some of the physical properties of a solution only depend on the number of particles that are present, and in terms of the solute and solvent there. So if you look at the definition of molality, we have a number of moles per kilogram of solvent. So that's a relative ratio. That's a ratio between the number of particles of the solvent versus number of particles of the solute. So number of moles, each mole has 6.02 times 10 to the 23, that many particles there. And kilogram, if you know what the solvent is, you can convert it into moles as well. Mass to mole, it's a mole to mole ratio there, and that's the relative particles of solute and solvent in that solution. So that concentration gives you that ratio there. So for the colligative properties, we refer to vapor pressure. When we define vapor pressure, it's when you have a volatile liquid, you put it in a closed container at certain temperature, that liquid will vaporize, generating a pressure, and that's a vapor pressure. So how does the vapor pressure of a solution, say water dissolved with some sugar dissolved in there, or water with some sodium chloride dissolved in there, how does the vapor pressure of that solution compare to pure water? Now in chapter 5, when we're talking about the vapor pressure of water, we have measured the vapor pressure of water in every temperature. And we know the vapor pressure when it's at 0 degrees, it's a certain value there. When it's at 100 degrees Celsius, it's 760 millimeter mercury. That's when the water starts to boil. So we want to take a look at it. How does the vapor pressure compare between the solution and the pure solvent, and also boiling point? Okay, boiling point is the temperature in which the vapor pressure of the liquid equals to the external pressure. We also introduced yesterday the normal boiling point. Normal boiling point by definition is when the external pressure is equals to 760 millimeter mercury. And a freezing point, that's another physical property, depends on the relative number of particles in the solution there, and then osmotic pressure. So we are able to quantify the changes for these four properties there, and these four properties are collectively called colligative properties of solution. And there are other properties involved, and it has something to do with the number of particles, relative number of particles of the solute and solvent. And the textbook mentioned that, but in this particular chapter there, we want to talk about these things there. Now, for the change in vapor pressure, if you want to quantify it, that follows the Rawls law. Now, we don't need you to do calculation, but this is something that we just want you to, that M word, memorize. So vapor pressure is the pressure exerted by the vapor when a liquid in a closed container is at equilibrium with the vapor there, and that's how we define vapor pressure. So if you have something dissolved in a pure solvent making a solution there, the vapor pressure of the solution is lower than the vapor pressure of pure solvent. So if you have a cup of water versus water with some sugar or salt dissolved in there, the vapor pressure of the solution with the sugar or salt dissolved in there is lower than the pure substance, than the pure water there, than the pure water there. Okay, so vapor pressure is lower when something is dissolved in the solution. Now, do we have to quantify? Well, we do have ways to quantify how much is the vapor pressure going to decrease, but in this case, we don't need you to do calculation. Just remember this conclusion: vapor pressure of a solution is lower than the vapor pressure of the pure solvent. Okay, and so that's the change in vapor pressure. Now, so the reason behind that is because the more solute particles present in the solution will result in a lower vapor pressure of the solution. Okay, so that's the change in vapor pressure. And now, out of those four colligative properties there, and we also talk about the freezing point. Now, the freezing point is actually lowered as well. So vapor pressure is lower for the solution compared to the pure solvent, and freezing point is also lower. We use the term freezing point depression. The freezing point of the solution is depressed because of the presence of the solute in that mixture there compared to the pure solvent. Now, this is something that we all have experience with, and if you put some water in the glass, and you put that glass in the freezer, now when water starts to freeze up, volume expands. We talked about that. The volume expansion is because of the hydrogen bonding. So hydrogen bonding, when the water freezes up, and it results in a larger volume there. Now, if you just have water in that glass there, this is what's going to happen there. When as volume expand, and then the container may be cracked. Now, if you put some antifreeze in here, well, that will keep the liquid in the liquid form without freezing up. So the application here is that you add some chemical in water, you prepare a solution. The solution will have a lower freezing point. As a result, the liquid will stay in the liquid form instead of freezing up. Now, if you have ever been to, in a cold winter day, if you have been to a harbor where the fresh water from the river meets the salty water from the sea, all you will see in the cold winter days, the freshwater part is freezing up. The seawater part is actually staying in the liquid form, and they're not freezing. So the reason for that is because there's a lot of salt dissolved in seawater compared to the freshwater from the river. So that's one of the things that that you will notice there. And also this past winter we got quite a bit of snow there. And every time when it snows, you see the trucks on the road and they spread sand and salt on the road. The reason that they put sand in there is to increase the friction, and the salt will dissolve in water, making water solution a solution containing salt. That will lower the freezing point of water by a couple of degrees there. In that case, now we'll keep the water in the liquid form instead of freezing up. So that's the application there. And one application that I could think of, is that I think it's the December of 2012. I want to go back to China and visit my parents, and I told you I have chickens. They need water. So I was thinking, well, maybe I can use the freezing point depression, add some salt to the water, and then while I am away, I can make a solution there. But the thing here is that how much temperature, how much the freezing, how much can you depress the freezing point depends on how low the temperature you want it to be. So I look at the weather channel there. The lowest temperature happens to be -8 degrees Celsius. So I did a calculation. I have a gallon water, and for a gallon water, 3.78 liter of water. If I need the freezing point of that solution to be below -8 degrees Celsius, and when I calculate the molality, I realized that I have to put more than 2 pounds of salt in that water, and I think my chicken would hate that, so it didn't work out, and I have to ask my neighbor to come over and change the water every day and replace the water and put it in there. So, but that's something that you can keep, and then you want to keep in mind there. And you can lower the freezing point solution by adding salt there. If it's only a couple of degrees, then you may be able to do that, and then putting some salt in there, and maybe lower the temperature by a couple of degrees there. So freezing point is lowered. How about boiling point? If you have pure water, we know pure water under normal condition, 760 millimeter mercury, pure water boils at 100 degrees Celsius. If you throw something in there to make a solution, the boiling point is increased. We can actually quantify the changes in boiling point and freezing point by using a mathematical equation. And the change in boiling point or the freezing point depends on the molality, the concentration of the solution. Okay, so this is another conclusion that we want you to remember there. When you have a non-volatile solute added to the solvent, and the key word there is non-volatile. And if you have, say, alcohol mixed with water there, when you start heating the solution there, alcohol will evaporate. And you end up with pure water in that case. Okay. So if you have salt or sugar, those are the non-volatile solute. When you put them in there, the solution will have a higher boiling point compared to pure water. It's going to be slightly above 100 degrees Celsius. And depending on how much you add in there, you can calculate and you can actually quantify the changes there. How do we do the quantification there? The change in boiling point or the change in freezing point is directly proportional to the molality of the solution. Now, Kb or Kf, and those are what we call the freezing point or boiling point constant for pure solvent. Different solvents will have a different constant, so we're going to give you these numbers here. Now, if you want to figure out how much change, you will have the example that I did with the water for my chicken in winter days there. I know the temperature is going to be -8 degrees Celsius, and that's the lowest temperature forecasted there. Now, the freezing point of pure water is 0 degrees Celsius. So the change will be 8 degrees, -8 from the temperature going from 0 degree to -8. The net change is 8 degrees Celsius. 8 degrees Celsius equals to Kf, and the freezing point constant for water, times the molality. If you know the volume of the water, you can convert it into mass there. And then you can figure out how many moles of salt that you have to dissolve in there. Well, if you know the number of moles, you know NaCl, you know the molar mass, and you can figure out how many grams you're going to put in. Okay, so these are the two equations that we can use to quantify the changes in temperature there. And in terms of the constant there, and again, Kf, and that's the freezing point constant, and Kb, that's the boiling point constant. Okay, and these are the numbers there. Okay, so for benzene, for carbon tetrachloride, for chloroform, for water, each has a different value there. And if we ask you to do calculation, and I know when you do Chem 102, and you will see this type of question on the ACS exam there, we will give you these constants there. You just need to know how to define molality, and you need to know that equation for the calculation. Okay, so there's no point to memorize all these equations, all these constants there will be given to you. And using these two equations there, we will be able to calculate the boiling point elevation or the freezing point depression. And we can also figure out the molality of the solution. We can also figure out the molar concentration, the molar mass of the salt, of the solute that we put in there. We'll give you some examples there. So this is the first example. Erythritol is a compound that occurs naturally in algae, and actually it's sweeter than the sucrose that we use there. So we can use that as a substitute for the sugar. It doesn't have as much calorie, but it tastes sweet. Okay, so in this case, we don't know, if we don't know the formula of this compound there, and then there's no way that we can figure out the molar mass of this compound. However, if you prepare a solution with water using this particular compound there, you can measure the freezing point of the solution. So in this case, if you dissolve 2.5 grams of this compound in 50 grams of water, you end up with the solution with a freezing point of negative 0.762. And we can ask you, we will be able to calculate the molar mass of this particular compound. So how do we go with this particular calculation? Now, the relationship here is that delta TF, that's the freezing point change between the pure solvent and the solution, water and the solution with this compound there, equals to KF times the molality, small m for molality. Okay, so this number here, we know the solution freezes at negative 0.762 degrees Celsius. So pure water freezes at 0 degree. This solution freezes at negative 0.762. So the difference is 0 minus negative 0.762. So here, this number will be 0.762. Now, that's in Celsius. Okay, now this number here though, equals to KF, KF of water, 1.86, times the molality. Now the molality is mass over molar mass divided by the kilogram of water in the solvent. Okay, we know the mass of the compound, we have 2.5 grams in there. Okay, we don't know the molar mass. So we plug in the gram 2.50 gram. And here we have 50 grams of water. We convert it into kilograms, 0.050 kilogram of water. And if you look at this equation there, everything of one quantity is given. So this is what we're looking for. The molar mass can be determined in this case. If you do the calculation correctly, 122 grams per mole. So this is one of the applications there. Actually, prior to, well, way back a couple of years ago, we were actually doing an experiment in the laboratory there, asking you to figure out the molar mass of an unknown compound by measuring the freezing point of pressure, which is a neat an experiment that we can do. We give you an unknown compound, we ask you to measure the freezing point of pure cyclohexane. We put the compound in there, dissolve it, measure the freezing point of the solution again, and you will be able to figure out the change in freezing temperature. And then KF of cyclohexane is given to you based on the molality. Well, you can figure out the mass of the solvent, cyclohexane, that you use, and you know the mass of the sample you put in there. The molar mass is the only M&M. So this is one type of calculation. And again, when you plug in the numbers there, and you just need to know the definition. How do we define molality? And if you know the definition, then solving this kind of question is really not that difficult. We've been working on more complex calculations than this, and so plug in the number, you get the M-now. Okay. Another type of questions here is we can ask you, if you dissolve 29.3 grams of sodium chloride table salt in 500 milliliter or 500 grams of water, what is going to be the boiling point of this new solution? We know the boiling point is elevated. Okay. So the constant for water, boiling point constant for water is 0.512 degree per mole. Okay. So we ask you, what's the new boiling point of the solution? Well, we know the temperature. We are trying, in this case, we will be able to figure out the change in temperature in terms of the boiling point based on the information given here. So, and delta T B, the boiling point temperature change, equals to KB times the molality. Okay, so KB is a constant given there, and that's 0.512 times the molality. Well, how do we define molality? Moles of solute per kilogram of solvent. Well, we have 500 grams of water there, so that's 0.500 kilogram of water. Okay, and then moles of solute, we have grams there, 29.3 of sodium chloride. Each mole is 58 point something, 0.5 grams. Okay, so here, through this particular calculation, you can see gram and gram cancels out, and you get per kilogram. Okay, so you end up with the change in temperature, and this will equal to 0.512. So the change in boiling point of this solution is going to be 0.512. What is the boiling point for pure water? 100 degrees. So the new boiling point of the solution would be 100.512. You add 100 to add this change to the boiling point of pure water, 100 degrees there. So the answer is going to be 100.512 degrees Celsius. So we can actually calculate what is going to be the new boiling point for the solution. We can do the same thing for freezing point, and just like if you know the change, then you can figure out what is going to be the new freezing point or new boiling point. And the calculation itself is quite straightforward. And knowing the definition, knowing the relationship there, you should be able to do the calculation. Okay. Another thing that here is that the mass of the ethylene glycol, the antifreeze that you use, okay, and when you add antifreeze to water, make a solution there. Now, how much do you need? Well, antifreeze, ethylene glycol, whatever you added in there, antifreeze is one of the applications. Whatever you put in water there, when you have the solution, the boiling point of the solution is going to be higher and will be increased there. Okay, so in this case, ethylene glycol, if you put it in water there, 125 grams of water, you add a certain amount in there. Now in this case, we know we want to have the boiling point elevated by 1 degree. The boiling point of pure water is 100 degrees. We want it to be 101 degree. So the change is 1 degree there. So again, delta TB in this case now be 1 degree. And that equals to 0.512, and this is the boiling point. Constant there, and then times the molality. Molality is the number of moles per kilogram. We have 125 gram of water, 0.125 kilogram of water. Okay, and then how many grams of ethylene glycol do we need to add in there? Well, we don't know. X gram times each mole is equivalent to 62 grams. Okay, so if you look at this equation there, the only unknown in there is your X, and that's the mass there. And you plug in the number and do the calculations there, 15 grams. Okay, so this is another type of calculation that we do need you to be able to do. And using the relationship of the freezing point of pressure and boiling point elevation equals to K times molality. When you know the definition of molality, when you're given the K there, you can do calculations. And of course, we can also ask you to figure out the constant, giving you all the other information there. Okay, so that's the type of calculation that you could you should expect when you deal with these different types of properties there. And the last colligated property that we want to mention here is what we call osmosis. Now, if you do, you can actually do this experiment at home. And get a fresh egg and cooked, of course. And you want to make sure that you wash the egg there. Now, if you take that egg, you put it into vinegar. Well, you can use pure vinegar, or white vinegar, or you can use pure acetic acid. Now, the acid will actually eat out or dissolve the calcium carbonate. One of the things that you may need to remember there is that when you for the solubility, rules of solubility that we talked about yesterday, this is something that you will solubility rules there, and something that you will see on the final exam there. And we talked about it in chapter 4. But I said you don't have to memorize them at that time. But when you prepare for the final exam there, you do need to pay attention to the solubility rules there. And there is a particular slide on Canvas there. When you click on the final exam there, you will see that slide. Okay, that's information you need to remember. If you don't want to memorize it, you can put it on your index card when you go to the final exam. Right? So osmosis here, and if you put an egg in acetic acid, you will be able to remove the calcium carbonate and remove the hard shell. Okay, and what's left there is the membrane wrapping up the whatever is inside the egg. That membrane is what we call the semi-permeable membrane. It will only allow water molecules to go in and out. But whatever is dissolved in the water there, whether you have organic matters, there are proteins and all the others, and it will not be able to come out. Okay, so in this case, after you remove the hard shell of the egg, if you put it into water, pure water, we would consider on the outside of the egg, if you put it in pure water there, and there's a higher concentration of water compared to what's inside. So in this case, osmosis will happen. The water molecules will make an attempt to get into the egg to equalize the concentration of water on both sides. The result of that, you see the egg start to swell because more water is getting in there. Okay? And then, however, if you take that same egg and you put it into corn syrup, now corn syrup has lower water concentration or lower content compared to what's inside the egg. So in this case, the water inside the egg will make an attempt to move out of it, and in order to equalize the water concentration, if you will. So you see the egg start to shrink. So this is the process of osmosis there. Osmosis is when you have two different solutions, two different liquids being separated by a semi-permeable membrane, which only allows the water molecules, small molecules like water molecule, to move in and out. Well, if you do that, if you mix them together, if you put them together, separate them by a semi-permeable membrane, the solvent will move from the higher concentration side to the lower concentration side in an attempt to equalize the concentration. Okay, so in this case, we have in this diagram there, we have the pure solvent on one side, on the left side, and we have the solution. And if you separate the two by a semi-permeable membrane there, and the water molecule will, in this case, solvent, will be able to move in and out in order to reach an equal concentration there. Okay, so the solvent molecules move from the pure solvent to the solution side in order to equalize with the concentration. And when that happens, you will actually generate a little bit of pressure, and this is what we call the osmotic pressure. Now, say if you have a semi-permeable membrane there, you make it a bag there, and you put some sugar solution in it, 95% water, 5% sugar. Okay. Now, if you take that bag and you dip it into pure water, on the outside you have 100% water. On the inside you have 5% water, 5% sugar, and then 95% water. So you have a lower concentration of water inside the bag. Now, if you do that, if you dip that bag into pure water there, over time you will see water molecules will get through the semi-permeable membrane, and then get into the bag there. You will see a water column being pushed up along this glass tubing there. The water column will actually generate a pressure. This pressure is what we call the height of the column, and we can actually calculate how much pressure we have there. So this pressure is what we call the osmotic pressure. It's a very important thing there. We can actually quantify the osmotic pressure. Pi equals to mRT. And this M is supposed to be molality, moles per kilogram of solvent there. mRT is supposed to be a small m there. R is the gas constant, T is the temperature. So you can see the osmotic pressure, we can calculate osmotic pressure and using this equation. Now, what's the importance of osmotic pressure? Keeping the solution that we're trying to mix with the same osmotic pressure. Well, the importance here is that if you ever notice that when you go to the hospital there and when they give you an IV bag, it's not pure water that they use to dissolve the drug in the IV bag when they put it on patients there. And it's always says 0.9% sodium chloride. The reason for that is because if you use pure water, okay, and you dissolve the drug, and when the drug gets into your bloodstream there, while pure water has a higher concentration of water compared to whatever is inside the cell. In that case, pure water will make an attempt to get into the cell to equalize the concentration. If that happens, then the cell is going to swell. And eventually, if you have enough quantity there, you're going to rupture the cell and you're going to kill the patient. 0.9% sodium chloride. 0.9% sodium chloride solution has the same osmotic pressure as the whatever is dissolved inside your cell. So using this particular solution and to dissolve your medication will prevent situations like higher concentration, higher osmotic pressure, lower osmotic pressure on the inside or on the outside of the cell there. So if you have a hyperosmotic solution there, and that results in the swelling of the red blood cell, that is dangerous. And then if you have hyperosmotic solution, that will result in the water inside the cell coming out. In both situations, we should be we should try to avoid both situations here in medicine there. And what we want to have is the isoosmotic solution. A solution with the same osmotic pressure, so that water will not flow in or out of the cell in an attempt to increase the volume or decrease the volume of the cell, or rupture the cell, or shrink the cell, or kill the cell. So osmosis has a lot of application in everyday life. And on a particulate level there, what happens here is that we know when we have ions, inorganic compounds dissolved in water there, those ions were actually hydrated. As a result, the size of the ions are actually bigger than just in water solution, than just the ion. So because of the attraction of the cations and anions for the water molecules there, we talk about water being a polar solvent. There's a positive end of water molecule, negative end of water molecule. Now, as the result of hydration, the ions becomes larger. As a result, they cannot pass through the little openings on the semi-permeable membrane. Only a water molecule can go in and out. Okay, so this is the application of on the particulate level there, and we can see why only solvent molecules are allowed to move in and out of a particular container there, separated by the semi-permeable membrane. And the pressure generated by that osmosis process can be used to purify water. Now, you've heard this probably on a regular basis there, reverse osmosis. Now, regular osmosis process there is that when you have seawater with a high salt content and you separate them with the semi-permeable membrane with fresh water, well, under the normal condition, the fresh water will make an attempt to get into the seawater side. However, if you apply enough pressure on the side with the seawater, you will be able to push the water to a water molecule through the semi-permeable membrane. And this is a water purification process. And some of the end-of-the-counter, end-of-the-sink reverse osmosis. When you have your water inline connected to that device, and then there's a water outgoing, there's another tubing connected to your faucet. When you turn on the water there, water from the city source or well comes in, and the pressure is being applied, and the pure water is being pushed onto the other side, and where you have your faucet connected to it. Now, the problem there is that this particular process actually removes everything from water, and what you got on the other side is just pure water. And you may think, well, isn't that a good thing? Well, it depends on what you need. If you just need water, well, that's a good thing. But the thing here is that for drinking water, the spring water actually have minerals dissolved in them. Those minerals are essential to human health. So if you use reverse osmosis, you're removing not only the things you don't want, also the things that you do want. The beneficial minerals dissolved in there will also be removed. So it depends on what you're trying to, how you look at the situation there. And reverse osmosis can be used to get pure water, but the result of getting pure water may not be exactly what you want in terms of your healthy diet and a good water to drink there. And also, if you try to do this on a large scale, like what you see in the picture here, removing the salt from seawater. This is the project that, in theory, it's a great idea, but the thing here is that it just costs a tremendous amount of energy. It's very expensive. And so some of the countries with along the coastlines of the Pacific and Atlantic Oceans there, and you have an unlimited supply of water there, but you can't really use them unless you remove the salt dissolved in there. And using reverse osmosis is one of the applications, one of the things we can do, but it's very costly as well, because you have to maintain that constant pressure, and you have to replace the semi-permeable membrane every once in a while. At least you need to backflush it. Okay, so that's the application there. Now, these are the colligated properties of solution there. Okay, when you have something dissolved in the solution, well, and then when you have that solution put next to a pure solvent there, and osmosis happens there. Okay, and when you have a solution versus a pure solvent, and the freezing point is depressed, boiling point is elevated, and the vapor pressure is lowered. So those are the things that, and some of the quantities there, we can use a mathematical equation to do calculations. Some of the things we just need you to remember or memorize. Okay, so that pretty much wraps up the topic in chapter 12 there. And make sure when you read chapter 12, there are many other topics covered in the textbook there, but try to focus on the topics discussed in class there, and make sure you, if possible, make sure that you work on the problem assigned in chapter 12 there. Okay, and it's 8:50, and I told your lab instructor that we are going to start our lab at 10 o'clock today. So I have roughly about an hour and 10 minutes. So we will take a short break, and after the break, we will take a look at chapter 15 and talking about the acid base. And that will conclude our lecture for this class, this semester there. So let's take a break, and then we'll come back and we'll start chapter 15. Now again, whatever is due today, and if you have it ready, you can put it in the folder, and if you don't, I will give you till Monday. Monday is the absolute deadline. I have to have everything. And those of you who are taking the exam in the test center, the last day to take the exam is Monday. Okay, you cannot go beyond Monday, and I need the result back at least by Tuesday, and so I can report the grade. Right? So we will have our final exam in class in this room next Monday at 8 o'clock. We'll have 2 hours. Everything in the folder is yours to keep. I just need you to put in whatever you need to turn in. Put whatever you need to turn in the folder.
Yeah. My leg is asleep. You did your lab, right? Yeah.
Wait, what? So if it's not positive or negative,
well, COCL, you got 24 electrons. In here is that a lot
blue skills nice.
Oh, okay. Well, in that case, you have pouring a negative. So whenever you have a double bond, as it is. Whenever you have a triple bond, whenever you have two single bonds.
Whatever it is, they
Well, that's at the other end.
So if it's polar, it's not.
Because these are for individual
At least that's what the
Yeah, it's just.
You don't do atoms. You just scroll through the
It's not that
structure and
Great, can only accommodate. So, yeah, how many we are?
She was being involved with know what the wood structure shows where the atoms bond, and he's looking to bond there.
No, this is for individual atoms. Yeah, we're on the.
But if we do, then
Hybridization, what's the hybridization on the same?
Really dark.
start our last chapter there, chapter 15. Now, those of you who are planning on taking Chem 102 this summer or later on, and chapter 15 in this textbook will be covered in Chem 102. And what we are trying to do in Chem 101 is we want to introduce some basic definitions. How do we define an acid? How do we define a base? And I was actually thinking about just when we adopted this textbook there. In chapter 4, we have a discussion about acid-base reaction in that chapter. And it was with mainly, chapter 15 deals with the behavior of weak acid and weak bases. But before you can deal with behavior of weak acid and weak bases there, you have to know how we define acid base. So this is, we're not going to cover the entire chapter, rather we're just going to cover the basic definition of the acid base there. And in terms of the homework assignment there, since you finish, we're going to be finishing this this particular chapter. Now there are questions assigned in homework number 3, and as I told you there, the minimum amount of work you have to do for homework number 3 is chapter 9, chapter 10, the first 2 learning objectives for chapter 10. 11, 12, 15, you can do as many as you prefer, or you can do as few as you want, or not doing them at all. But again, as I always try to tell the class there, when I teach a class there, exam is very important. What you will be tested is very important. But more important than that is the topics that we cover in there. So you don't just study for the exam, rather you need to make sure that you pay attention to the materials that we cover in this course there. And even if you are not being tested, when you don't have the time when you're preparing for the final exam there, I understand you can skip these things for now. But after the final exam, please make sure you take the time to read through it. Make sure you understand these basic definitions. And the reason I want to emphasize that is because I talk to other faculty members on a regular basis there, and they always say, when we get into chapter 15, this particular topic in Chem 102, when we started talking about acid base, and students in the class there, most of them will say, well, we've never had this before. I said, we have them in Chem 101. We talk about acid base. So this is something that you do need to know when you get into Chem 102, something that you do need to pay attention to. Okay, so talking about the acid base there, we have to know how do we define a particular compound as an acid. And also, since chapter 15, the focus is going to be on the behavior of weak acid, all we want to know, how do you differentiate, how do you define what's a weak acid, what's a strong acid there. And what happens when you dissolve an acid in water and the acid gives out something, what do we call the leftover? And we use the term conjugate acid and conjugate base to describe whatever is left after the donation or reception of the proton there. So we want to give you an idea of what is a strong acid and strong base. Now, when you talk about the acid there are only 6 known strong acids. Everything else would be a weak acid. Okay, so here, hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, HI. Okay, nitric acid, perchloric acid, citric acid. These are the only known strong acids. And this is something that I actually need you to memorize. We will ask you questions on the final exam. Which one is a strong acid or which one is a weak acid? Well, if you know, these are the only 6 strong acids, and everything else will be a weak acid. Okay, so this is a table in chapter 15, and we need you to remember there. And when you look at the review sheets and study guide for the final exam there, we actually talk about that. What are the 6 strong acids? Well, you need to know their name, you need to know their formula. And these are the only 6, these are the all the strong acids that we know of. Okay. Everything else will be a weak acid. Vinegar, acetic acid in vinegar, that's a weak acid. Okay. Ammonia, that's a weak base. So we want you to, when you look at the acid there, we try to put a different color on the hydrogen there. And we will talk about that definition. And when we talk about the definition of the acid there, we will show you the importance of that colored hydrogen there. You have to have at least one hydrogen attached to the most electronegative elements in the molecule in order to qualify for an acid there. So these are the 6 known strong acids, and everything else will be a weak acid. Now, how do we define acid? How do we define base? Well, in chemistry, in the area of chemistry, there are many different ways to define a particular chemical as an acid or a base. One of them is what we call the Bronsted-Lowry definition. And also, when you get into organic chemistry, you will hear Lewis definition, the same Lewis, Gilbert Newton Lewis. Will give you the Lewis structure and all that theory there. So we have Lewis acid and Lewis base. And Bronsted-Lowry definition focus on what happens when you have a compound that can be called acid. An acid is a substance that can donate, meaning given out, a hydrogen ion. Well, hydrogen ion, H+. Hydrogen has one proton, one electron. When you lose that one electron, the only thing left is the proton. So you see the term proton for H+, and you also see the term hydrogen ion. They mean the same thing. Okay? So acid would be something that can donate a hydrogen ion. So you have to have a hydrogen ion with you to begin with. Otherwise, if you don't even have a hydrogen with you, you cannot donate hydrogen ion. So that's how we define an acid. Bronsted-Lowry definitions as a substance that can donate a hydrogen ion is an acid. Okay. Examples of acid there: HNO3, nitric acid, one of the 6 strong acids. Acetic acid, CH3COOH. Now, there are 4 hydrogens in acetic acid. Only this hydrogen is responsible for the acidity of the compound. HNO3. Now, hydrogen is attached not to nitrogen, but to oxygen. Hydrogen is attached to, if you draw the Lewis structure there, you will see hydrogen has to be attached to the most electronegative elements. Okay, so that's the acid there. Now, looking at nitric acid versus nitrous acid, HNO3 versus HNO2, you can see hydrogen is attached to the oxygen. Hydrogen is attached to the oxygen here. Because nitrogen is group 5A, oxygen is group 6A. Electronegativity-wise, oxygen is more electronegative. It's on the right side of the periodic table. Okay, so hydrogen has to be attached to it. And if you look at the acetic acid there, CH3COOH. Now, this hydrogen is attached to the oxygen. This hydrogen is responsible for the acidity or the acid property of the acetic acid there. So in this case, an acid, put it in red, you have to remember this. Acid must have a hydrogen bounded to an element of high electronegativity value. Okay, so when you have 2 different types of elements in there, and with a hydrogen, which one is the hydrogen going to attach to? Well, look at the group number for those 2 elements there. Whichever has a higher group number, meaning a higher electronegativity value, hydrogen is going to go with them. Okay, so hydrogen must be attached. You must have at least 1 hydrogen attached to the element, the most electronegative elements in there. You can have more than 1, like sulfuric acid, H2SO4. In that case, both hydrogens are attached to oxygens in there. Okay, so different oxygens, you have 4 oxygens in there. So both hydrogens are attached to oxygens, and both hydrogens are responsible for the acidity. Okay, so again, you must have at least 1 hydrogen bounded to an element with high electronegativity value here. Now, the question here is that when we look at different species in chemistry there, we must be able to differentiate whether a particular species is going to be an acid or not. So nitrate ion, can this be a Bronsted-Lowry acid? Well, the definition says something that can donate hydrogen ion. We don't even have a hydrogen ion in there. It cannot be an acid or a Bronsted-Lowry acid. Bronsted-Lowry acid. So this one cannot be NO3. Cannot be. HNO3 is an acid, but NO3 minus, that's not an acid there. We will have a proper term for the NO3, nitrate ion, when we get into the next section there. So talking about the acid, the other side will be base. How do we define a base? Acid is defined as something that can donate hydrogen ion. Well, base is substance that can accept. So give and take is always happening simultaneously. When someone is giving out something, whether it's a proton, hydrogen ion, or electron, there has to be someone out there that can take them in. Okay, so Bronsted-Lowry definition says the substance that can accept a hydrogen ion is a base. So examples of base, we can have hydroxide ion. Okay, hydroxide ion we can have ammonia. Now, what is in common between these two? Well, if you draw the Lewis structure there, you have lone pair of electrons on oxygen, an atom with high electronegativity value. If you draw a Lewis structure for ammonia, you have a lone pair on the atom with high electronegativity value. So the key here, in order for something to qualify as a Bronsted-Lowry base, a Lewis structure indicates a base must have at least one lone pair of electrons in order to accept the proton. Now remember the proton, H+. It has an empty orbital, no electrons. Now if you have a lone pair of electrons, H+ come in, that lone pair of electrons will be shared between the hydrogen and the atom with the high electronegativity value. You form the chemical bond there. Okay. Without the lone pair, they will not be able to accept that proton there. So this is how we define base. Okay. So the definition here is that now if you have ammonium NH4+, or if you draw the Lewis structure for NH4+, you ask, why does it bear a positive number, a positive charge there? Well, ammonium is, nitrogen is 5. Nitrogen is a group 5A, so 5 valence electron. 5, 6, 7, 8. Total of 8 valence electrons, all are accounted for. Now if you bring in a proton, you get 8 protons here plus 1 more proton. So you get now 9 positive charges, only 8 electrons, which each bear a positive charge. So can ammonium act as a Bronsted-Lowry base then? Well, in this case, there is no lone pair of electrons. There's no way you can put another proton on this molecule or on this ion. It cannot be a Bronsted-Lowry base. So you got to know the definition. How we define the Bronsted-Lowry definition is one of the definitions. Then we have Lewis acid, Lewis base, Arrhenius definition, Arrhenius acid, and Arrhenius base. And each definition focuses on a different perspective. Okay, so Bronsted-Lowry definition focuses on the transfer of the proton. If something can donate a proton, that's an acid. If something can accept a proton, that's a base. Okay, so there are substances in this world that can both donate and accept protons. Now we have a term for those substances that we call them amphoteric. Water is an example. H2O. Depending on who water is with, water can either donate, well, you got 2 hydrogens attached to oxygen, so water can either donate protons. Since oxygen has 2 lone pair of electrons, in the water molecule, oxygen has 2 lone pair of electrons. Water can also accept a lone pair of electrons. So example here, if you have hydrogen iodine, one of the 6 strong acid, when you dissolve that in water, well, in this case, this guy has a stronger ability to donate the hydrogen ion. In this case, water will have no choice but to take it in. Water starts with as a neutral molecule, and when you take in a proton there, you end up with H3O plus positive charge. So in this case, water is acting as a base. Water is accepting protons. But if you have a sodium chloride dissolving water, now chloride ion now has a negative charge in there. Okay. Hydrogen, you got a hydrogen on the water molecule there. Chloride ion is so electronegative that they will try to grab the hydrogen from water. In this case, water is donating. Water is donating the proton. So in this case, water is acting as an acid. So water can be viewed as, can act either as an acid or a base. So this is a special, very special property for water there. And that's why acid can dissolve in water, base can also dissolve in water. A very important feature there, amphoteric, that's the term that we use. Something that can act both as an acid and a base. Okay, so what happens if something donates electron or accept electron? What happens to the electron? What happens to the species that result in the either the donation of the electron, hydrogen ion or the acceptance of the hydrogen ion? We use the term conjugate acid and conjugate base to call those species after the transfer of the proton is finished. So conjugate base would be a substance formed by the loss of hydrogen ion from an acid. So if you have an acid give out a proton, what's left is what we call the conjugate base. So an acid, the counterpart of the acid after the donating of the hydrogen ion, the counterpart is called conjugate base. Okay, and then for acid here, if you have water, for example, removal of the hydrogen ion resulting in OH minus. OH minus is what we call the conjugate base of the acid being water in this case. Now, what happens to the base that accept the proton? After accepting the proton, so substance formed by the addition of the proton is what we call a conjugate acid. Okay, now, example here, if you have ammonia is a base with a lone pair of electron. If you put a proton to it, you end up with ammonium NH4+. This is your conjugate acid. So keep in mind, conjugate acid and base, conjugate base and acid, these things comes in pairs. After you give out something, whatever is left, after you give out the proton there, whatever is left is called conjugate base. Now, you start with yourself, and then when you accept the proton, you end up with conjugate acid. Okay, so these things are always come in pairs. So Bronsted-Lowry definition for acid and base basically indicates for every acid there has a conjugate base. Every base has a conjugate acid. Okay, and they all come in pairs. And here in this case, if you try to dissolve ammonia in water, and you end up with ammonium hydroxide, so this is a base, you have its conjugate acid. This is an acid, you have the conjugate base. Okay, solution is slightly basic, or the solution of the ammonia is slightly basic because of the presence of this thing here. Okay. So the relative strength determines whether you have an acid solution or basic solution. We'll give you the definition of acid solution, acidic solution or basic solution in just a little bit. And so we ask you, now that we know what happens in the Bronsted-Lowry definition here, so we ask you, we need you to be able to identify what we call the conjugate acid or conjugate base there. So what is the conjugate base for HBr? HBr is one of those 6 strong acids there. So what's the conjugate base for it? Definition, the species after you donate the proton. So when you give out as HBr, when you give out H+, what's left in there? Br, there has to be a charge. Br, negative, thank you. So that's the conjugate base. What is the conjugate acid of OH minus? H2O. You gain, after gaining another proton there, you have OH minus to begin with, you put another hydrogen in there, hydrogen ion bears positive charge, negative charge, neutralizes, you end up with H2O. So what's the conjugate base for phosphate ion? One of those 16 polyatomic ions that I asked you to memorize in chapter 2. What's the conjugate acid for HeO4 3 minus? I will wait to 10 o'clock until you give me an answer.
HeO4 2 charge.
Thank you. So you add a hydrogen ion to it, a positive charge, 3 negative charge, you end up with 2 negative charge. So HPO4 2 minus. And this is something that we want you to be able to do. What's the conjugate base for HClO4? Perchloric acid. ClO4 minus. Now you get it. So what's the conjugate acid for HSO4 minus? H2 minus. Well, conjugate acid actually acid obtaining hydrogen there, so H2SO4. You're adding a hydrogen to it. Now the same species there, we can ask you, what's the conjugate base for that? Well, that's when you have SO4 minus. So you need to know how we define acid and how we define base, and how do we define conjugate acid and conjugate base. Conjugate base is the result after the acid gives out the hydrogen ion. Conjugate acid is the result of the base acquiring the hydrogen ion there. And then some of the species there, you see, they can act either as an acid or a base. So water is not the only substance that's amphoteric. And HSO4 in this case, HSO4 minus can act either as an acid or a base. And they can take in a hydrogen ion, acting as a base. Again, they can also donate whatever they have there, one hydrogen attached to it, and that's an acid there. Okay, so definition, this is what we're trying to focus on. And again, when you get into Chem 102, your instructor is not going to spend any time talking about conjugate acid, conjugate base. They will assume you know what they are. So they are going to use the term when they start talking about the acid base there. So what's the conjugate base of the NH3? What's the conjugate acid of NH3? You need to know the definition. Okay, so this is what we want to introduce in Chem 101 before you get into Chem 102. That's our first learning objective. We give you a lot of definitions there. You got to know the definition. Second, well, next logical question there. Second learning objective there is, how do you measure? How do you determine what we call the acidity or basicity of a solution when you have an acid base? When you deal with acid base, we use what we call a scale. We call it pH. Well, the P scale, by definition, is the negative log of whatever quantity. So pH is the negative log of hydronium ion concentration, hydrogen ion concentration. pOH, by the same token, will be the concentration, negative log of the concentration of hydroxide. So we need you to be able to do calculation, figure out the pH and pOH if the concentration of the solution is given, or be able to figure out the concentration if the pH is given. Okay, so first of all, how do we define acid base? And we give you the definition there. But something interesting about water, aqueous solution there, is that water can actually act either as an acid or a base. Now, what happens if you put two water molecules together? Well, there is what we call an autoionization of water. Not on a large scale, on very small scale there. This is what's happening there when you have two water molecules close to one another. One water molecule will be able to take the hydrogen ion from the other, forming a hydronium ion, and then what's left for the other water molecule would be the OH there. So you end up with an acid and a base with neutral water there. Now, thank goodness this is not happening on a very high level there, or rather it's actually happening at a very low level. The water is a very weak electrolyte. Now we say pure water does not conduct electricity simply because we don't have a whole lot of charged ions, H3O plus or OH minus. Okay. And in this case, how low is the autoionization and the level of autoionization? About 2 molecules of water out of about 1 billion water molecules will go through this process. So you don't really have a very high concentration of the hydronium ion, hydroxide ion concentration. However, this is very important. When you have water, water can dissociate, can go through the autoionization. At a certain temperature, the concentration of hydronium ion, H3O plus, and hydroxide ion, OH minus, is fixed. Okay. The product of those two concentrations remains at a constant, remains as a constant when the temperature is fixed. So for water or any aqueous solution, the concentration product between hydronium ion and hydroxide ion is a constant. At 25 degrees, that constant equals to 1.00 times 10 to the negative 14. Now, this constant is called autoionization constant of water. Very important number to remember, 1.00 times 10 to the negative 14. Okay. Now, in any aqueous solution, if you know the concentration of this, you can figure out the concentration of this, or the other way around, because the product of these two equals to a constant. This is very much similar to that wavelength and frequency relationship to the velocity of of light. Lambda times nu equals to the speed of light. So the concentration multiplied by one another equals to a constant. So if you know the concentration of one species, you know the concentration of the other. 1.00 times 10 to the negative 14 divided by whatever whatever it is given, and you find out the concentration of the other species there. Okay. So in this case, hydrogen ion concentration or hydronium ion concentration and hydroxide ion concentration are inversely proportional to one another. One is lower, the other is higher. The product ends up with a constant there. Okay. Now, solutions are classified based on the concentration. Water solutions are classified based on the concentration of hydronium ion and hydroxide ion. If you have a higher concentration of H3O+, we say the solution is acidic. If you have a higher concentration of OH-, we say the solution is basic. If you have equal concentration of both, no, the solution is neutral. Depending on the relative amount of these two species there, we have these three different terms to describe the property of the water solution: acidic, basic, or neutral. Okay? So in this case, how is acidity, basicity measured? Well, acidity or basicity of an aqueous solution is measured by what we call a pH value. pH value, or the P lot there, pH or POH. pH by definition, that's a definition there, that's a D word. Okay. pH by definition is the negative log of the molar concentration of H3O+. POH, negative log of hydroxide ion concentration. So if we give you the concentration of either of these species there, all you need to do is to take the negative log of that concentration. Now we'll give you the pH or POH. And Kw, in this case, equals to the concentration product of these two species, and that equals to a constant there. Now if you take the negative log on both sides of the equation, you get negative log of this times this. If you remember your logarithm, which I hope you did, well, negative log of this times this equals to a negative log of this plus negative log of this. Well, negative log of this is pH. Negative log of this is POH. So pH plus POH equals to the negative log of this number. Negative log of this number, log 1 equals to 0, log 10 to the negative 14 equals to 14. pH plus POH equals to 14. That's always the case in any aqueous solution. Whenever you're dealing with water solution, pH of the solution plus POH of the solution equals to 14. So if you know pH, you know POH, because they add up to a constant, 14. Okay, so how do we define whether a solution is acidic or basic? If the pH is less than 7, the solution is said to be acidic. If the pH is greater than 7, the solution is said to be basic. If pH equals to 7, well, the solution is said to be neutral. POH, however, is just reversed. Now this is actually a litmus paper. We can use, well, you hear this term, a litmus test. Litmus test is that when you have a litmus paper, when you dip it into an acidic solution, it will give you a pink color. Okay, you will be able to tell, using the litmus paper there, you will be able to tell whether a solution is acidic or basic. And when you dip it in there, pink color, acidic, blue color, basic. Yeah, so you use that term these days, and the next presidential campaign has started already. Many people jump in, though some of the people, you look at them, they shouldn't really be in public office, but they jump in anyway. And there are a lot of litmus tests for those people there. And you ask them a question, depending on how they answer the question, well, you know where they stand. Where does it come from? Chemistry. Okay, so chemistry has everything to do with everything that we encounter in our everyday life. So this is how we define acidic and basic solution there. So again, the pH scale. What does the pH number imply? Well, in this case, the lower the pH, the more acidic the solution. Okay? And the higher the pH, the more basic the solution. That's what the pH is all about. Remember, the pH is the negative log of the concentration. And the lower the pH, it means negative log, the higher the concentration of the hydronium ion. The higher the pH means the lower the concentration of the hydronium ion concentration there. So the normal range for pH is 0 to 14, but pH could be a negative number. You could have a negative number. Okay. Now, pH equal to 0 is when the concentration of hydronium ion equals to 1 moles per liter. 1 moles per liter, well, that means log 1. Log 1 equal to 0. Okay, so pH can be a negative number there, because if you have a 0.1 molar HCl solution there, for example, the concentration would be 0.1. Well, negative log of 0.1, well, that will give you actually, a positive of pH is going to be a positive one there, because there's a negative sign to begin with. And when the concentration is higher than 1 molar, you could end up with a negative number of the pH solution there. Okay, so the negative number indicates a very acidic solution, very high concentration of hydronium ion. And then larger than 14, that means it's a very basic solution. So the scale that we need you to remember, for anything that is acidic, pH has to be less than 7. Anything above 7, the pH, anything to be basic, and the pH must be above 7. Right at 7, that's neutral, a neutral solution there. Okay, so in this case, neutral solution means you have equal concentration of hydronium ion hydroxide. Each one equals to 1.00 times 10 to the negative 7. 10 to the negative 7 times 10 to the negative 7 equals to 10 to the negative 14. Constant there, Kw. pH plus pOH needs to be 14. So the pH for neutral solution would be 7. And then for the acidic solution, that means you have a higher concentration of hydronium ion and then lower concentration of hydroxide ion. So pH is less than 7. Remember definition, negative log. There's a negative sign in front of it. So the concentration-wise, when pH is lower than 7, that means the hydronium ion concentration is more than 1.0 times 10 to the negative 7. The other is lower. Hydroxide ion concentration is lower. For basic solution, it's just reversed. Okay. So these are the basic definitions that we want to give you. How do we do calculations there? Well, once again, how do we classify acid solution, basic solution? These are the pH values that we use to classify solutions into acidic or basic there. So, question we can ask you here. A solution has a hydronium ion concentration of 5.5 times 10 to the negative 5th. What is the pH of the solution? Well, in order to do this calculation, we got to know the definition. Definition of pH, negative log of the hydronium concentration. So pH in this case equals to the negative log of 5.5 times 10 to the negative 5. Okay. Now if you know your logarithm there, this is a negative log of 5.5 plus negative log of 10 to the negative 5 there. Now log 10, when you move the exponential number to the front there, so this is basically plus 5, log 10 equals to 1. So basically this is 5 minus log 5.5. And log 5.5, 5 minus log 5.5. You can do that on the calculator there. Now, or if you don't want to do all this, simply plug this number in your calculator. Take the next log of that number there. That will give you the answer. I thought I had the answer on the slides there. So it's going to be 4 point something. Okay, log 5.5 is probably somewhere around 0.3, 0.4. So 5 minus log 5.5 is going to be 4 point something, meaning this solution is basic, right? Less than 7, supposed to be acidic. We got it. Okay, so the significant figures in pH there, and one thing that we do want to point out there, when you talk about the concentration of the hydronium ion, hydroxide ion there, the coefficient, well, we're talking about a relatively low concentration when you use the pH to measure the acidity or basicity there. So if you have one digit, one sigfig in the coefficient, the pH value will carry 1 decimal point, 1 decimal place. If you have 2 sigfig in the coefficient in the concentration, pH value carries 2 decimal place. Okay, so that's something that you want to pay attention to. And you have to watch for the sig fig when you deal with any measurements in chemistry and physics there. Then you have to pay attention to the sig figs there. So that's a relationship there. And then we can ask you to do questions there. If we give you the hydronium ion concentration, we ask you the pH. But if we give you the pH, we also need you to be able to figure out the concentration. So this is the reverse. pH is 6.64. What is the concentration for the molarity of this solution? Well, if pH is 6.64, oops. X is what we're asking you there. The inverse log of negative 6.64, or 10 to the negative 6.64 power, that will give you the answer. Plug in that number in the calculator there, and you should end up with an answer there. And it's always going to be coefficient times 10 to the whatever the power. Okay, so the calculations that we want you to be able to do here is that if we have a pH, hydronium ion concentration, 1.6 times 10 to the negative 3, what's the pH? Well, you take the negative log of that number, and this is what you end up with, 2.80. Okay, and then if we ask you to find the pH for giving you the hydroxide ion concentration, now this is a situation you need to remember. Hydroxide ion concentration, we can simply take the negative log of this. That will give you pOH. If the question is asking you to find pH, pOH, 14 minus pOH will give you pH. So two different ways to do that. You can either figure out, based on the concentration of hydroxide ion, you can figure out the concentration of hydronium ion and then take the negative log of that, or you can simply calculate the pOH first and then subtract it from 14. That will give you a pH of 10.5 there. Now again, this indicates the solution number 3 is acidic. Solution number 4 is basic. 7 is the watershed, if you will. Below 7, that's acidic, and above 7, that's basic there. Okay, other calculations there, we give you the concentration, we ask you to find the, we give you the pH, we ask you to find the concentration. The inverse log of a negative 8.79, or 10 to the negative 8.79 power, will give you the answer. Plug in the number there, and this is what you're going to get. Now, here you get 8.79, 2 decimal places there, so the coefficient should bear 2 sig fig. On the other way around, when you have 2 sig fig here, the pH value has 2 decimal places there. Okay, and this is what we need you to be able to do to calculate the pH. Because when you get into Chem 102, pH calculation is going to be a big part of chemical equilibrium. So chapter 15 will mainly focus on this calculation. Giving you a weak acid or a weak base, giving you the equilibrium constant, we ask you to figure out the pH. Basically, if you need to figure out the pH, you have to be able to figure out the concentration first and then take the negative log there. Okay, so that's what Chem 102 is going to be focusing on for this particular chapter. And then in Chem 101, all we want to do is to introduce how do we define acid, how do we define base, how do we figure out pH, and if the concentration is given, or how do we figure out the concentration if the pH is given. Okay, you will be getting into the details in Chem 102. We'll get into the details about the behavior of acid base, of weak acid and weak bases there. So here are the examples of the type of calculations that we have here. Okay, you need to be able to do these calculations, and that's pretty much all we want to talk about in chapter 15. So this is really not an entire chapter there. We only scratched the surface of the chapter. And this is the end of the chapter 15 there. And again, when you study for the final exam there, make sure you click on final exam on Canvas and do the review questions there. And click on exam number 1, number 2, number 3, and do those review questions there. Quiz 4 quizzes that I gave you. Okay, make sure you answer those questions there. And the final exam is going to be in this classroom on Monday, June 29th, and from 8 to 10, 2 hours there. And as always, thanks for a great semester. And as everything must end in this. Good luck with your Chem 102 if you're taking Chem 102. On Monday, either, you know, we can do it now, and you can do it.
Yeah, it's like an antidote if you're like on a bad trip,
It's real tough.
For 5 weeks, you did a really good job packing it all in. Thank you, thank you.